But it is my great pleasure to welcome Dr. Erin May, and thank you so much again for speaking with us this week. Dr. Erin May got her PhD from the University of Michigan in 2019, where she worked on a variety of ground-based observations in 3D climate models of exoplanet atmospheres. And she is currently a postdoctoral fellow at Johns Hopkins Applied Physics Laboratory, and now spends most of her time thinking about space-based observations of exoplanets. She is involved with Spitzer, HST, and soon to be JWST data analysis, as well as mission development for future exoplanet and exoplanet analog observations. And her main focus nowadays is a uniform reanalysis of Spitzer phase curves to enable population level studies of atmospheric circulation, which I think you'll be hearing about today. So Dr. May, thank you so much for speaking with us, and I'll turn it over to you.
Thank you so much for the introduction. I'm going to get screen sharing started, hopefully.
Looks good on my end.
Okay. So I do have the chat window pulled up. If you have questions, feel free to put them in the chat throughout it. If I don't see them, Joe, you're welcome to interrupt me so that I can answer questions throughout the talk. Yeah, so I'm Erin May. I'm just down the road from Goddard at Johns Hopkins Applied Physics Lab. If you're not familiar with APL, we're fairly new to the exoplanets game as of about 3 years ago, but we have a growing group of exoplanet scientists. We're technically separate from Hopkins. We're just kind of associated in name only for the most part. We're located in Laurel, Maryland. So yeah, today I'm going to talk a lot about Spitzer observations of phase curves and phase curves in general. I'm going to start with some introductory material to phase curves. So if you're an expert in phase curves, feel free to use this time to take a bathroom break and get more tea or coffee, because I know a lot of times we're jumping between meetings really quickly. But before I get into this introduction of what phase curves are, I want to do a brief overview of some of the amazing science Spitzer has done for exoplanets. You know, I'm always surprised when I'm in a room with people who don't think about Spitzer all the time, how few people are actually aware of what Spitzer did to get us where we are today in our field. So first of all, Spitzer is responsible for the very first spectrum of exoplanet atmospheres. So around the same time, observations came out of HD 209-458 and HD 189-733, kind of the first two stereotypical hot Jupiter planets. And this was the first time that we detected molecules in a exoplanet's atmosphere. These spectrum are specifically for HD 209, but 189 look fairly similar. And it showed us that Spitzer was capable of a lot more than we thought, and that there was a lot of interesting science to gain from studying atmospheres and being able to observe them directly. So this was a really exciting time in exoplanet science. And actually that same year, we got the first map of an exoplanet. This is HD 189 again. Essentially, it's just an inverted phase curve, but it showed us where the hottest parts of a planet were and corresponded fairly well with what model predictions were. And then more recently, Spitzer was instrumental in confirming 5 of the TRAPPIST-1 system's planets. Very different planets and hot Jupiters. They're all very much Earth-like or sub-Neptune-like. This is really important for advancing terrestrial planet and habitability work, because suddenly we had this really great nearby system of terrestrial planets, partially thanks to work done by Spitzer. Now, but I'm here to talk about phase curves. So during the warm Spitzer mission, so this was after Spitzer ran out of coolant, and we were no longer able to use it at longer wavelengths, Spitzer observed nearly 60 phase curves of 31 exoplanets. And this comes out to about 3,000 hours of observations dedicated just to phase curve observations of exoplanets. Now, back before we knew just how successful JWST's launch was, and we expected it was only going to last for about 5 years for the primary mission, 3,000 hours would have been about 10% of that primary JWST mission time. So Spitzer's going to remain, even in the era of JWST, an absolute treasure trove of exoplanet data. There's absolutely no way that JWST is going to spend 10% of its time staring at exoplanet phase curves, as much as we would like it to. And even if it did, it's probably not going to dedicate that time to going back and looking at a lot of the same targets that Spitzer did, and we already have these observations from. So even as we're about to start getting JWST data in just under 2 weeks, we can really expect that the Spitzer phase curves are going to remain instrumental in our understanding of exoplanet atmospheres. And I want to point out this 3,000 hours is just phase curves. I didn't even try to count up the number of hours dedicated to eclipses and transits separate from the phase curve observations. So this is where I'm going to get into what a phase curve is and why do we care. So now you can go take your break if you know what a phase curve is. So there's a few main points that we can, of observations we can get out of phase curves. The first is secondary eclipse. So typically when we observe a phase curve, we always get 2 secondary eclipses to bookend our observations. And there's a couple of reasons for that. So during secondary eclipse is when the planet goes behind the star, and the amount of light that is missing from our observation of the system corresponds to the day side flux of the planet. And this is specifically at these infrared wavelengths where we're measuring the day side flux during secondary eclipse. This is important because the amount of light that we're observing from the system during secondary eclipse is only the starlight. And that gives us a baseline for the system. So we're able to tell how much light that we're observing at any other point in time comes from the planet versus the star itself. So when we observe 2 secondary eclipses on the edges of our phase curves, we're able to have that baseline of where the stellar flux is to help with our detrending in case there's any long temporal trends in the data sets. The next part of a phase curve I want to point out is that transit, which happens when the planet crosses in front of the star, and the amount of light that's missing in this case is just the ratio between the planet and the star radius. Now, just because it's a phase curve doesn't mean that we aren't able to also use transits for more like what we typically use them for with transmission spectroscopy. We do still get that absorption through the planet's atmosphere. So we're able to use transits taken during a phase curve to help extend transmission spectroscopy observations from telescopes like Hubble or Kepler. And then the reason that we call them phase curves is because we're observing every phase of the planet. So as the planet orbits the star between secondary eclipse and transit and back around again, if these planets are tidally left, at every point in time, we see a different side of the planet. And as that planet rotates, we see more or less of the day, that permanent day side and permanent night side. We can take the peak of the planet flux and compare it to the minimum of the planet flux and look at this phase amplitude because it gives us information about how heat is being transported from the day to the night side, which tells us things about the efficiency of how heat is moved in the atmosphere. If you have a very thick atmosphere, typically it's going to be more efficient at moving heat around, and your day and night side are going to be closer in temperature to each other, even if one side of them is that permanent day side and one side is never getting any starlight. The atmosphere is just helping to equilibrate things around the planet. But if you don't have an atmosphere, or the heat is just not being efficiently moved around, you can end up with a very steep amplitude, a very strong difference between the day and night side of a planet. This is actually one of the ways that people have tried to use to determine if a terrestrial planet has an atmosphere, for example. How strong that phase amplitude is helps us constrain that. The last main measurement we can make during an observation of a phase curve is what's called the hotspot offset. So if you're trying to move heat from the day side to the night side, you end up with very strong winds due to that temperature differential in the atmosphere, really forcing the winds to move heat around the planet. In this case, your hottest hemisphere is not going to align perfectly with your day side of the planet. It can be shifted slightly due to those winds blowing it around, and you end up with your hottest part of the planet being observed slightly before you go into secondary eclipse. And just how offset that is tells us things about the strength of the winds in the planet's atmosphere. So the reason that we make these observations with Spitzer is that Spitzer's an infrared, or was an infrared space telescope. So Spitzer IRAC, the main instrument that we use for exoplanet science, had 4 observational channels. Once we entered the warm Spitzer mission, we no longer could use channels 3 and 4 because we didn't have coolant. And so we were left with just channel 1, which is centered at 3.6 micron, and channel 2, which is centered at 4.5 microns. And both of these have band passes of about 1 microns. These channels roughly correspond with the hottest or largest emission from a planetary black body. So it makes Spitzer an excellent candidate for observing these phase curves. Spitzer, during the warm mission, primarily observed phase curves of hot Jupiters, one, because they're really hot, two, because they're really large compared to a small planet, which makes these signals like the phase variance, the hotspot offset, larger signals and easier to measure. So on the left, I'm showing you all the planets that have been observed in phase curves with Spitzer. So we have equilibrium temperature on the y-axis as a function of orbital period. And these stars are the phase curve observed planets. And you can see they really all pile up at the short orbital periods, mostly just because the longer the orbital period, the longer you have to stare at the object, and you end up getting some additional systematics. And also just because of the larger signals from the higher temperatures and larger bodies. So all of this sounds great. It sounds like Spitzer is the perfect telescope to study planetary emission. But unfortunately, like most telescopes to date, Spitzer was not designed with exoplanets in mind. So Spitzer observations, the raw flux is often a mess. And I don't know if anyone is able to draw on the screen. If you have an annotate option, I invite you to use it and try and label these phase curves and tell me where you think eclipses is happening and where you think the transit is happening. I've covered up the x-axis on purpose here. Is anyone even able to annotate? I'm not sure what the permissions are.
You should be able
great.
to if you
See,
oh, there you go.
see some labeling happening. Yeah, the right side is a little bit easier. So looks like we've got some people labeling some transits. Where do you think eclipses are happening? I think that's the funnest part to try and label. If you have no idea, just take a wild guess. No one wants to. Oh, we have a label for an eclipse. Okay, I'm going to reveal the answer so we don't spend too much time here. But you all were correct. The orbital phase of 1 or 0 is where transit occurs. So we have, let's see, can I clear all the annotations? Cool. Okay. So an orbital phase of 1 or 0 is where the transit occurs, and that's occurring in the center of these plots. Maybe I should have shifted them to make it a little bit harder. And then eclipses occur at a phase of 0.5. And I told you that they bookend our observations. So maybe that was a little bit too easy where one of them is going to occur near the beginning, and you do see a little bit of a dip here. But if you didn't know that eclipse should have occurred at the beginning of the observation, that dip could easily be confused with a systematic. And then on the left, it's just like, you know, what is Spitzer even doing? We have these weird periodic sinusoidal variations in flux that are much larger than any astrophysical signal that we would expect. So the reason that the observations look like this coming straight out of the telescope is that Spitzer systematics are dominated by this thing called intrapixel sensitivity variations. So if you're an observer, you may be familiar with interpixel variations, which is just a fancier name for flat fielding. So when we flat field, it's because every individual pixel measures a different response to the same amount of light. Intrapixel variations are changes in the pixel response depending on where the center of light falls within a single pixel. So if we zoom in on one pixel on this imaginary flat field, the sensitivity is actually changing depending on where you are within that single pixel. So to correct for this, to first order, we just have to measure the center X and Y position of the star's light in a given exposure within that single pixel and keep track of it throughout the observation so that we know not only what pixel we're in, but where within that individual pixel we are. Now, it's much harder to know a priori what this intrapixel effect is. For a flat field, we can just evenly illuminate the detector and to tell how much light each pixel was measuring. For intrapixel, we need to shine a light at different points within a single pixel. we can't be evenly illuminating the entire pixel. We need a star or a constant light point source to move around within a pixel to map it out. So it's not something that we can just put a lamp on a telescope to help us figure out. So this is an example of what the mapped out pixel looked like for channel 2 from Ingalls et al. In 2012, where the amount of flux that was measured depended on where you fell within the pixel. So the color here is the relative flux measured as a function of the sub-pixel scale on the detector. So this is the first order sensitivity effect or systematic effect with Spitzer IRAC, this intrapixel sensitivity variation. This isn't the only main systematic. We also have the fact that the shape of the PRF or the PSF, essentially how spread out the light is, also changes as the centroid drifts from the center of the pixel. So if the center of your starlight falls in the center of your pixel, you're going to measure the highest amount of light, and the shape of your light on the detector is going to be a circle. If the center of your light falls on the sides of the pixel, you're going to measure less light, but the shape is also going to be an oval. These are two confounding effects that make observations with Spitzer quite annoying and make it hard to understand what the underlying astrophysical signal is. So we need a way to remove both of them before we can get to that astrophysical signal. So this is an iterative process like we would for any fitting, and it's all happening with something like an MCMC. We start with our raw data, select an astrophysical phase curve model. These are typically things like combinations of sinusoids to explain how the light from the planet changes as a function of phase. We then fit a polynomial form to the Gaussian widths of our PRF, so how stretched out it is in both X and Y. And then we take the residuals between that phase curve and polynomial and our observed data and spatially bin them onto a grid of detector subpixels. That map that is created can then be interpolated back onto the exact centroid location of each exposure to try and fit this intrapixel variation. And then we iterate until we arrive at a map and phase curve and everything that perfectly describes what's going on with our observations. This is called self-calibrating the data. So we're relying on the data to tell us what the detector sensitivity was. That requires well-behaved observations where the centroid revisits the same sublocation of the pixel multiple times. So we're able to disentangle that subpixel effect and the astrophysical signal. In the end, we're able to fit all of these wiggles and we can just divide out that component that comes from the systematics to get that pretty phase curve that you may be used to seeing. All of this sounds great and easy, not terrible to deal with, but you may have noticed that the intrapixel effect and the Gaussian widths both depend on where you are within the pixel. And in fact, these two parameters are highly correlated. So what I'm showing here is a really close zoom in on one phase curve observation, doesn't matter which planet. On the bottom is the relative centroid position in Y, and the top is the relative Gaussian width, how stretched out this the point spread function was in Y. And you see that they're very correlated. They have peaks in the same spots, troughs in the same spots. So if you have two systematic models that essentially use the same parameter to fit, you are likely to end up with degeneracies between the two of them. For this Gaussian width in the centroid, in this data set, we're able to show with a continuous wave transform that these features are occurring on the order of tens of seconds. So as long as we have data that's has a higher temporal resolution than the size of the features of about 10 seconds, we should be able to disentangle them. But if we had data that was temporally binned to data points larger than this average feature size, we've essentially smoothed over any small variances between the two, and it's harder to fit them independently. This is important because Spitzer datasets are very large. The largest that I've dealt with has almost 2 million data points in just one phase curve. So in order to just deal with them computationally efficiently, we need to bin them temporally. So it doesn't take so long to do our analysis. But if we bin them, we risk the ability to actually detrend them properly. And in fact, we showed in our 2020 paper that binning removes the features that are necessary to fit them, and we actually end up with inconsistent phase curve fits. So the top row is if we're just using BLIS mapping, or the method of self-calibrating the data to create a map with intrapixel sensitivities. And the bottom, we've also added that detrending with the Gaussian widths. Left, middle, and right are just different astrophysical phase curve models. Don't worry about that part. But the main thing to point out here is if we're using both of those two systematic methods and we bin our data, so each color corresponds to a different amount of temporal binning, we end up with inconsistent phase curve fits, depending on our choices for how we analyze the data. So if you have two functions that are degenerate, or two parameters that are degenerate, we typically want to find a way to hold one of them constant. And this is where the idea of using calibration data for the telescope comes in to help build up what the sensitivity of the detector is itself. So we expanded on the map that was generated by Ingalls et al. 2012, and specifically we used the same data reduction techniques that we apply in our Spitzer data pipeline. So it's important that we use, for example, the same method of finding the centroid or the observations, so we can one-to-one compare the centroids of a fixed sensitivity map to that of our observations. So now we have this map that tells us how sensitive each subpixel is on the detector, and we can essentially just divide it out of the data in advance like we would with a flat field. And in theory, we should only have the astrophysical signal left behind, but we are talking about Spitzer, so occasionally we have other weirdness left in our data that we have to deal with. This map is only applicable to 4.5 microns. I'm not going to talk about 3.6 microns in detail for the sake of time. I will put up a teaser. 3.6 micron detector has significant time and spatial variability. If you want to learn more about it, please ask me later. But we actually can't use the same method at 3.6 microns, unfortunately. Most of that data is just a lot more unreliable for a variety of reasons. But the takeaway number one that I want you to leave with from this talk is that don't temporally bin your Spitzer data, and probably any data that you have strong systematics in, unless you have a really strong understanding of what those systematics are doing. And we've developed this updated detrending tool for 4.5 micron Spitzer data that hopefully gets around some of the degeneracies in Spitzer data analysis. I do want to point out that this map, when we apply to WASP-43b, our results are more consistent with 3D circulation models. The reason I bring up WASP-43b is this is a prime example of how data that at first glance looks well behaved can actually give different results depending on how that same data set is analyzed. So I'm showing phase curve results for the same data set, 4 different groups, 4 different methods, reducing it. There's a different night side flux measured in every single one of these phase curves. And there's 2 sets of phase offsets or hotspot offsets that are measured. All of these are the same data sets to begin with. They've just all been treated differently in the data reduction process. The newest results using our fixed sensitivity map on the bottom are more consistent with general circulation models than the original Stevenson et al. 2017. So I'm going to ask you to ignore the top panel for now. I'll talk about that later. But on the bottom, we're showing the phase curve amplitude as a function of planet or radiation temperature. The dashed and solid lines are GCM predictions from Mike Roman's 2021 paper. Dashed are clear and solid are cloudy, and then the color is the gravity of the planet. The gray circle with the red outline is the original Stevenson et al. 2017 phase amplitude measurement, and our new reduction using our fixed sensitivity map, which helps account for systematics more efficiently and effectively, is more in line with model predictions for a planet similar to that. So this is promising, but really the main takeaway from this slide is that data reduction is a complex process. It's important that we're aware of how our systematic methods are impacting the data. And when we're entering the era of JWST data, we really want to be sure that we understand our systematic models and that different systematic models do converge to the same results, or we use some type of tool to understand the best results from a variety of systematic models at once. So this is a major reason why many groups are moving to multiple independent reductions of a data set within a single paper, so we can have some consistency and better understanding of what the true astrophysical signal is when you have large systematics. We do expect that some of the JWST detectors may have this intrapixel effect, but it's going to be a spectroscopic effect, and it may overwhelm the signal as well. But back to Spitzer land, with all of this in mind about how the way you treat the data matters, we decided to perform a uniform reanalysis of all of the Spitzer phase curves with more care given to each individual data set while treating it the same way as we've treated every other data sets, so that when we're looking at trends, we know that these trends are from the planet itself, and it's not just systematic scatter, it's actually astrophysical. So the second takeaway I want you to leave with is that different data reductions result in different answers for Spitzer phase curves. This has been seen for HST observations as well, and it will likely be the case for JWST observations in the coming years. So be cognizant of how data's been analyzed. If you see something that's making an extraordinary claim, see if every systematic method gives you that same result before you believe it. Uniform methods can mitigate some of this, specifically when we're looking at trends, because we know they've been treated all the same, but absolute values are really hard when systematics are really large. So in our effort to do a uniform analysis of all 60 exoplanet phase curves, we're starting with the planets that hadn't been analyzed as of a couple of years ago. So to start, I want to talk about WASP-76b. This is a inflated ultra hot Jupiter. It's about 2200 Kelvin. It's really famous for the ground-based high resolution observations that detected signs of iron condensation on the night side of the planet, or this idea of iron rain. There's a lot of wonderful ground-based high resolution papers discussing it, and there's probably even more since I made these slides. So I apologize if I forgot your favorite one. But the main thing is that there's been a lot of molecules detected in the planet's atmosphere from these ground-based observations. The reason we wanted to go after it with a phase curve is that theory suggests that this planet needs a hot internal temperature to inflate the planet to its large radius. If you have a hot internal temperature, that's going to be most obviously observed on the night side of the planet because it's not overwhelmed by the irradiation from the star. So in order to measure the night side emission of the planet and determine if it's likely to have a hot internal temperature, or to confirm that, we need a phase curve observation. You mentioned at the beginning how phase curves give you that baseline in the eclipse measurement, so you know the exact contribution from the sun and can determine what's coming from the planet itself. So as of now, phase curves are the only confirmed tried and true way of doing this. There are other methods coming up to hopefully be able to give us night side observation or measurements without the full phase curve measurement. I'm not going to talk about that here, but obviously we went after this, or in the past it was gone after with Spitzer, and we're finally sitting down and analyzing these phase curves. Before I get into the results, I do want to mention that this is from a co-first author paper. So please email me if you have questions about how to cite it properly. Currently, unfortunately, it won't show up as a proper citation in AAS journal formatting, but it can show up properly in archive versions so that both first authors get the credit. Okay, so I spent a lot of time already talking about how we do this data analysis, so I'm not going to bore you with more of that, and I'm getting into the results. So for WASP-76b, we had 2 phase curves at 3.6 microns, which is the problematic channel, and 1 at 4.5 microns. Now WASP-76 has a nearby companion that's 0.3 pixels away, so we had to actually apply 2 fixed sensitivity maps to that 4.5 micron data set to account for the location of WASP-76 and the location of the companion star as well. If you're interested in that, please check out the paper where we talk about that a little bit more. But the main point of this paper is we were able to take these phase curves and compare to model predictions to see, does this planet have the hot interior that we think it must have to be so large and inflated? So we used the MIT GCM, and we ran models considering a cold interior, a hot interior, and for both of those, 5 different drag strengths of the atmosphere. So what we're looking at are maps of brightness temperature, so that's latitude versus longitude, and the color corresponds to the temperature of that region of the planet. On the left are our cold interior runs, and on the right are our hot interior runs. As we move from top to bottom, we're increasing the strength of drag in the atmosphere, which just corresponds to a shorter drag timescale. Some things I want to point out, which are the expected results of a model suite like this, is that you end up with stronger winds when you have cold interior models, just because there's less heat on the night side. So there's a stronger temperature differential that's forcing the winds to move heat away from the day side. Another expected result of a model suite like this that I want to point out, when you have strong drag, so a time scale of drag less than 10 to the minus 5, these couple bottom rows, you're characterized by primarily a day to night flow. This includes winds that are flowing just over the poles, just away from the subsolar point in any direction. And that's because the winds have been essentially dragged to zero along the equator. But when you have weak drag, so these couple rows at the top, you're characterized primarily by equatorial jets blowing heat around the equator. Typically, it's commonly seen kind of like chevron pattern. We have a hot equator. So we take these models and we post-process them to give us what the observed phase curve would look like in our Spitzer bands. And what we found was that the cold interior strong drag model is best matched for phase curves. So on the left, we're looking at the 3.6 micron data compared to the hot interior models on the top, the cold interior models on the bottom, and then the same on the right, but for the 4.5 micron observations. The purple lines correspond to the strong drag, so a shorter drag timescale, and the yellower lines correspond to weak drag, or the longer drag timescale. You can see that specifically for 4.5 micron, the hot interior is just too hot on the night side, and the cold interior is a much better match to our observed night side emission. Specifically, also these stronger drag, darker purple lines. Now I point this out because this is interesting because the Erin observations that are the reason that the iron drag has been induced require low drag in the atmosphere. But I want to note that we're observing different regions of the atmosphere, and I'll get into why that's an important caveat in a couple slides. But our phase curves do rule out weak drag from just these observations. Okay, I do want to say that none of our models can explain all of the phase curve parameters. So what we're looking at here are 4 key parameters coming out of the phase curves as a function of the drag timescale. So the lines correspond to model predictions. Solid lines are cold interiors, dashed lines are hot interior models. The yellow or goldish lines are 3.6 micron, blue or purple are 4.5. And that solid line or solid bar going across is the observed value of that parameter. So if a line passes that bar going across or crosses through it, that tells us there's a model that can explain it within our set. So importantly, the cold interior models, so the solid lines, don't, sorry, I need some water. They only moderately agree with our 3.6 micron observations. I do want to say this isn't uncommon. 3D models typically don't agree well with Spitzer observations. We can place some blame on Spitzer and the models themselves. Some caveats in our specific models is that they are cloud-free. This might not be an issue because it is an ultra-hot planet, and we expect it to be less cloudy. Our model is double gray, which means we only consider a radiation band in the optical and the infrared, and that's all. And we know that things like optical absorbers can affect the day to night redistribution. It may be something important to consider in 3D models. Our models also use a uniform drag timescale. And we know that things like magnetic drag will be spatially dependent, and magnetic drag is likely to be really important for ultra-hot Jupiters. And I'll talk more about that, I believe, on the next slide. Okay, So we did measure essentially no hotspot offset, and this agrees with previous ultra-hot observations for WASP 103 and WASP 18. And there's recent theory work by Haley Beltz et al. That suggests that these ultra-hot planets might have really strong magnetic drag, and that could explain the lack of a phase curve offset. So this is a figure from that paper. Again, these are the temperature maps, so latitude versus longitude, and color is temperature. As we move from left to right, we're increasing the magnetic field. When you increase the magnetic field on a really hot planet, you have more ionization, which interacts with that magnetic field and causes drag, which slows the equatorial winds. So I don't know if you can see on the screen share, there are these gray lines on each of these panels, which corresponds to the wind speed and direction. So on the 0 Gauss, and I should say moving from top to bottom, it's just moving deeper in the atmosphere. So we're going to focus on the top panel. On the no magnetic field case, you have this equatorial flow pattern like we typically see for hot Jupiters. And as you get it to a stronger magnetic field, you end up with just winds flowing in every direction away from the substellar point, including over the poles. And you have no phase curve offset in these models when you have a strong magnetic field. Something that is probably the case for these ultra-hot planets. Another thing I just want to point out quickly is that we have reason to be suspicious of our 3.6 micron data. It wasn't super high quality, but if it holds true, WASP 76b, as of the publication, was one of the first planets that had confirmed a day side inversion with no night side inversion. This is expected from models because the night side is so much colder, but this was one of the first times that it was confirmed observationally. So the takeaway number 3 is that we need better models, and this might be controversial, but I will point out that I am sometimes a modeler myself. So I'm also to blame for the lack of physics in some of the models. 3D GCMs are computationally expensive to run, and the more physics you add into them just makes them slower. So we always need to make some simplifying assumptions. But there are some things that we might be that should be included in future models, so we can be sure we're explaining all of the physics that can happen in anything from a colder hot Jupiter to an ultra hot Jupiter. So some things that we're thinking about including or actively working on including in future models include things like radiatively active clouds. This is important for the cooler hot Jupiters where you have feedback happening between the cloud decks and the atmosphere itself, and that can affect the day to night recirculation as well. Stratospheres or inversions sometimes aren't included in the 3D models. And then also things like hydrogen dissociation and magnetic drag, which I just showed you that previous work that's starting to include that. Hydrogen dissociation itself can really lead to a reduced day to night contrast, so that's something that we should also including in our models for these ultra hot planets. So with all of that in mind, we need to, 1, finish analyzing all of the unpublished Spitzer phase curves and then go back and redo all of the previous ones. And 2, we need to get better models that when we're starting to look for trends and planetary parameters, we're able to determine if the trends we're seeing are matched by models, or maybe there's still some systematics we need to consider in our data sets. So there's a lot of unpublished Spitzer phase curves. So I showed you this plot at the beginning. This is our phase curves, the stars compared to the background population of planets. As of a year ago, these yellow stars were the unpublished ones. So about half of them actually remained unpublished. In our most recent work, we added 5 to the category of published for a total of 8 phase curves. All of them had equilibrium temperatures of about 1300 Kelvin. And the reason we selected planets with similar equilibrium temperatures is that allows us to remove temperature as a dimension in trends, look for secondary parameters that control things in the atmospheres. So again, I'm not going to spend a lot of time or any time talking about the data analysis. We used the same methods I discussed at the beginning, and you can see the paper for more. But as is typical, the data quality ranged from very well behaved, what was Spitzer even doing? So these are plots showing the centroid of the X and Y as a function of time in the top part of each subpanel, and the bottom is the raw flux. So you can see some of them, the centroid really jumped around a lot. Some of them it was fairly smooth and constant. All of these just add different intricacies into the way in which we have to deal with the data. So we did use the fixed sensitivity map method when it was applicable. These are the outputting sensitivity maps for those detector locations in those observations. For the 3.6 micron observations, as I alluded to, we can't use a fixed map method because the detector seems to have spatial and temporal variability in how sensitive it is. Qatar 2 observations don't actually overlap with our fixed sensitivity map. The pointing was really off for some reason in that observation, which means we had to use self-calibration there as well. WAS52, that data set was just not great. So we had to use additional sources of detrending in addition to our fixed sensitivity map. WAS34 was what was Spitzer even doing? This was one of the longest phase curves observed at like 4.5 days. And the longer you stare at an object with Spitzer, for some reason, the worse quality the data gets. Qatar 1 and WASP-140b had very well-behaved data sets, though. So, as you saw in the previous slide, our analysis was as uniform as allowed by the data. And we set out to do a uniform analysis. Obviously, there's times where things don't work out, and you have to treat each data set a little bit differently because of the way the Spitzer systematics are so large. So these are the resulting phase curves. I'm not going to spend a lot of time on this slide either because I want to get into the population level trends. I'm going to point out that WASP-140 has a very slight eccentricity, and it seems like it only recently arrived at its orbit, and we have reason to believe that it actually might not be tidally synchronized because we're measuring a westward phase offset, which is opposite of what we would expect. So we actually exclude this from a lot of our trend fitting because we're specifically looking or interested in tidally locked planets, and we can't confirm that WASP-140 is. And then WASP-34, which I mentioned was one of the longest phase curves observed, is a grazing event, and you can see these characteristically U-shaped eclipses here. We actually also had a data downlink gap in the middle of it, which is kind of unique to the observation. It was just so long that Spitzer couldn't store all the data on board. And of course, that introduced additional systematics because the telescope was moving around. But trends, maybe why you're all here. So we do find evidence for a trend of increasingly eastward phase offset as a function of orbital period. And I'll say we don't only find that in just the full population, but also in our 1300 Kelvin sample. So on the top, so on both panels, we're plotting phase offset versus orbital period. In the top, we're fitting a trend to just the now 4 remaining planets in our 1300 Kelvin sample, the solid ones. On the bottom, we're fitting it to everything with the exception of WASP-140. Color just corresponds to equilibrium temperature. And there is statistical evidence that there is an increasingly eastward offset in that 1300 Kelvin sample, but it is heavily driven by just this one data point, WASP-34, because we don't have a lot of long orbital period observations because it just takes a lot of time. So this trend, though, it's dynamically interesting because theory doesn't predict that there should be a dependence on rotation rate for phase offset. And if we think of all these planets as being tidally locked, orbital period is essentially just a proxy for rotation rate. What theory does predict is that the hotspot location should be driven by the ratio between the radiative and advective timescales in the planet's atmosphere. So these are 2 timescales that control things like how heat is redistributed and how strong the winds are in the atmosphere. We know that rotation rate does not strongly affect the radiative time, or doesn't affect the radiative timescale. So the existence of this trend suggests that the rotation rate does have implications on the wind speed, that advective timescale essentially, in these tidally locked hot Jupiters. So if there's any high resolution ground-based observers out there, I encourage you to go observe, try and measure wind speeds in hot Jupiters that have a variety of orbital periods and see if there's a trend of stronger wind speeds with larger orbital periods, because this would be an independent confirmation of this phase offset versus orbital period trend that we're starting to see here. I will point out that most of the other planets in the sample have not been analyzed with our uniform method. Some of them were analyzed before advancements in Spitzer systematic removal methods very long ago. So we are working to reanalyze a lot of these so we can clean up these trends. We also looked at what's called apparent heat redistribution in the planet's atmosphere, which is essentially the day-side temperature divided by the equilibrium temperature to the fourth power. And then where this is plotted as a function of equilibrium temperature. The lines here are models from Parmentier 2021. The thicker lines correspond to the bolometric emission from these observations, and the thinner lines correspond to just the 4.5 micron channel emission, which is what these observational points are. Same as before, where the dashed is cloud-free and the solid is cloudy. Our new sample of planets are the 5 darker shades here, and the rest are the background population or the literature values. First thing I want to talk about on this slide is that our 1300 Kelvin sample spans a wide range on this plot, suggesting that this heat redistribution has to depend on more than just equilibrium temperature, which is something that a lot of models are primarily looking at. We compared this to additional third parameters like phase offset, orbital period, gravity, and we didn't find any parameter that clearly showed a reason why the planets with the same temperature are having different apparent heat redistributions. So that's something that we're hoping that additional models can look at, and adding new reanalyses will help us clear up. The other thing I want to point out is that when we were calculating this apparent heat redistribution, we didn't always know what values, stellar values, that the literature observations used to convert from flux to temperatures. So our equilibrium temperatures that we used to compute the heat redistribution are not necessarily the same, based off the same values in the papers, because those numbers just weren't reported. So there is going to be some scatter, some vertical scatter in this plot that is just due to these non-uniform methods, and we're hoping to clean this up in the future so we can definitively say which planets have really strong redistribution and which ones don't, which helps us understand what's going on in the atmosphere. And then the last thing I just want to talk about is that WASP-52 and Qatar-1, so the 2 planets from our sample that are hotter than even the bolometric emission predictions for these planets, is very interesting because these are below the temperatures where we would expect MHD or magnetic effects to begin to affect the day-to-night heat transport. So we can't just explain this away as saying, oh, there's unmodeled MHD effects, and we've got cloudy models on here. So we're not entirely sure why these planets are appearing warmer on their day sides than models are predicting. So I'm going to come back now to this plot that I showed you before with the models from Mike Roman's 21 paper. I've also added the models from Parmentier 2021, which are the same models from the previous slide. And I want to point out that our offsets do not generally, observed offsets generally do not agree well with model predictions. In general, so this is the top panel, there seems to be some kind of systematic offset between observed phase curve offsets and model predictions. We do have maybe a better agreement with the Parmentier models, but one thing in particular at the hotter temperatures, I showed you that work from Haley Belts, which shows that these hotter planets, when they're hot enough to have magnetic effects, those magnetic effects will drag the offset to 0. And these models aren't including those magnetic effects. So if we had a suite of models that included magnetic effects at the appropriate temperature, we might start to see more agreement between offsets, measured offsets and predicted offsets. In the bottom panel, when we're looking at the phase amplitude as a function of equilibrium temperature, the amplitudes of our new observed or newly reduced phase curves do agree well with model predictions. And in fact, we're seeing that 3 of the planets potentially have clear atmospheres according to these model predictions, and 2 of them likely have cloudy atmospheres according to these model predictions. The rest of the planets, there are those same potential inconsistencies, because it's not always clear if these literature values are reporting the amplitude based off of the maximum emission, or the hottest hemisphere and coldest hemisphere, or the day side hemisphere and the night side hemisphere, which can be shifted if you have a large offset. So we're hoping to clear up some of that with our reanalysis with the uniform methods as well. And the last trend I want to talk about actually is this this weird thing that we noticed, that there might be some trend of offset versus gravity, because in our new sample, we saw that 2 of the planets with the higher offsets had lower gravities than the ones with the westward or low phase curve offsets. So we looked at an offset as a function of gravity. This is color coded by equilibrium temperature, and the blue are our new observations, and everything else is the literature values. And if I just draw some really horrible trend lines on here that I apologize for, we're seeing that as temperature increases, offset trends in offset versus gravity flatten off. And this is something that we're possibly attributing to the fact that as you get to a hotter temperature, you have these magnetic effects, and that dominates what drives the offset. The offset is just driven to 0 because of those strong magnetic drag. For the cooler planets, there's something else causing there to be dependence of gravity, or offset depending on gravity. This is something that we're hoping models will be looking at more in the future. And as we begin to reanalyze some of the data sets, maybe we'll see clearer trends, or maybe this will just disappear. So the final takeaway is that the scatter and the different trends might not be astrophysical. This is the same as takeaway number 2. What I want to highlight here is that we're working on this uniform reanalysis to mitigate some of the scatter, to understand what the actual astrophysical trends are and what is from systematics themselves. I like to end everything with a talk and a tweet. So if you took a nap until this point, this is all you need to remember. We have a funded program working on this, which we're adding additional physics into the 3D model that we use. We're working on the uniform reanalysis. So stay tuned for more work from our team over the next few years. And I'm happy to take any questions.
Thank you so much, Erin. That was a great talk, and thank you for dealing with detectors that don't want to cooperate with us. So yeah, if anyone has any questions, please feel free to raise your hand, or you can post your questions in chat and I can read them off. I guess I will, let me see if there's any right now. I'm not seeing any just yet, but just to kick it off, kind of in the last couple of slides there, when you were talking about the magnetic field strength effects, I just wondered if you could kind of give us an indication of how far away we are in terms of the models and also the detector limits on pulling out the strength of a magnetic field from the phase curve.
Yeah, so from the modeling side, magnetic drag is implemented in a few GCMs. It's just not typically always used because the models are much slower when you have this non-uniform drag. I think the problem of trying to use the phase curves to actually measure the magnetic field will certainly be the precision. And I don't have a number off the top of my head to tell you about, what photometric precision we need to be able to measure a magnetic field strength. I think all at the moment we're able to do is really say this planet has to have magnetic drag to explain the fact that there's no phase curve offset. That's a number that maybe I should sit down and calculate. I know, for example, in Haley's paper where she has all of these GCMs with different magnetic drag, and she's calculated the phase curves as a result of them. I think you're really just going to be able to place kind of like a lower limit on the magnetic field, because at some point you can't drag the winds any slower. They're already gone. So the magnetic field could be larger. We just can't tell because we've had observations.
Gotcha. Very cool. It looks like we have a question in chat from Emily Gilbert. She is wondering, how well do we know the eclipse timing prior to taking measurements? Do we need RV measurements first to get the orbital parameters?
Yeah, so there are some phase curves where I think they didn't know great before they were taken, but generally the phase curve observations would start several hours before we would expect the eclipse to come. And these hot Jupiters should all be on very circular orbits. There are some well-known ones that are on more eccentric orbits, and those ones I'm sure they had to better constrain the actual eclipse timing in order to get things to line up properly. But for these typical hot Jupiters, the circular orbits, I mean, it should just occur half an orbit away from the transit pretty easily.
Gotcha. And another question I had, going back to kind of the first part of your talk, is when you were talking about all these techniques that you're developing to do these calibrations. I don't know the history of Spitzer or looking ahead to JWST, but what's kind of the cadence of having to redo these calibrations? Like, are these detectors, when they age, when they, after, on the order of months or years, are you seeing that you have to do quite a lot of retooling of the pipeline and the calibrations?
So yes, scarily yes. So some of the last phase curves observed by Spitzer, so WASP 34, which I mentioned, was a very horrible data set to deal with. That was, I think, actually the last phase curve observed by Spitzer. Some of these ones observed towards the end of its lifetime were just wild. The pointing got really, really bad, pointing stability. And so you ended up moving around a lot more on the detector, which causes, if you're not revisiting the same spot, you can't tell what's astrophysical and what's systematic. And then one of the channels on Spitzer, we saw temporal variability in the sensitivity, and we're not exactly sure where that's coming from. We're working on trying to figure that out. It's possibly that was degradation of the detector over time. So it's likely that we'll see some of these same effects with JWST, the detectors just kind of declining over time. Luckily, maybe, I don't think we're going to be able to do a fixed mapping method for JWST phase curves because they're going to be spectroscopic. So you don't have a single point source that you can map out the detector with. But like with Spitzer observations, the systematic methods kind of evolved really quickly at the beginning. Really quickly reached a point where, okay, this is our best method. But by that point, a lot of phase curves had already been observed and nobody's gone back and redone them. There's been a long lead up to actually getting JWST data, and a lot of people have been working really hard on understanding what the main systematics are likely to be. I think we're going to be ready to kind of hit the ground running and hopefully have a really good handle on systematics for JWST from the beginning. Cross our fingers, of course. We don't know what's going to happen when we get the real data, but it should be less problematic than Spitzer data for sure. Maybe.
Let's all hope.
I don't want to promise anything, but we'll see.
Yeah, I think we're all going to be finding out very soon. So exciting to hear. Does anyone else have any other questions for Erin before we end? We're just about on the hour. I'm not seeing any. So Erin, thank you again so much for coming out and talking with us today. This is really cool work, and excited to see what happens next with looking at JWST and everything else coming down the pipeline.
Thanks
Unintended.
for having me.
Yes, well, take care, everyone. Thanks everyone for coming out today. We'll see you all soon. Thanks again, Erin.